One of the biggest problems faced by today's generation is the growing need to find a renewable way of making energy and relying less on burning fossil fuels. One method that we will look into involves harnessing the energy created as a vehicle passes over a speed bump. This energy can then be stored and used to power streetlights later on. We decided to look into this technique and see if it was a worthwhile, feasible way of making energy. So how does the speed bump generate energy?
Electricity is generated as a vehicle drives over a raised speed bump. The weight of the vehicle causes the bump to compress, and a lever is thrown and begins to turn a flywheel. The flywheel then spins, using energy from the vehicle which would otherwise be lost, to power a generator and produce electricity. This generator is linked to a lithium battery, which stores the energy produced and then, via an inverter, provides the streetlights on the road with electricity.
We decided to look at speed bumps on a road in a residential area where the speed limit is 20 miles an hour. This will mean that the road is busy, and a busier road will result in more energy created. Also, we are assuming that the mass of the car is 1,500 kilograms, as this is the average mass of a family car. Also, the speed bump is being modelled at 10 centimetres tall. Now let's have a look at the maths behind it.
Firstly, we want to calculate the energy produced by one car going over the speed bump. We do this by using the equation work done equals force times displacement, where force is the average mass of our car, 1,500 kilograms, times by gravity, and the height of the speed bump is our displacement, which is 0.1 metres. This gives us 1,471.5 joules. However, we need to factor in energy loss. We're assuming that 20% of all energy is lost, for example as heat energy and sound energy. We can now work out the power, using the equation power equals work done over time, where time is 2 seconds as the speed bump is compressed for 2 seconds as the vehicle drives over. This gives us 588.6 watts. Now, we want to find out if this is enough energy to power the street lamps on the residential road for 12 hours. We found out that it takes 35 watts to power a street lamp. Using the equation work done equals power times time, this means that it would take 1,512,000 joules to power one street lamp for 12 hours. If we divide this value by the amount of energy produced as one car goes over the speed bump, we get the value 1,284.4. Therefore, we need at least 1,285 vehicles to go over one speed bump to power one street lamp for 12 hours. Using the fact that on average we have 250 vehicles per hour driving along our residential road, which equates to 3,000 per day, we can find out the total energy is actually 3,531,600 joules. If we divide this by the amount of energy needed to power one street lamp for 12 hours, we get the value 2.34. Therefore, we can deduce that one speed bump can power at least 2 street lamps on our residential road.
This method of creating electricity is very green as it does not directly require the combustion of fossil fuels. However, as the energy is provided by vehicles, you could argue that more fuel is burnt in order to clear the speed bumps, so it is not entirely carbon neutral. One positive of the speed bump is that it recovers some energy that is usually just lost from the vehicle into the surroundings. The general idea of energy generating speed bumps is very personal. Not only does it save on electricity costs, but it also is used to reduce speed and increase road safety. Most of the negatives come from the production of the speed bumps, as fuel is required to extract the raw materials and construct the mechanism. The biggest issue is cost, as each speed bump has a value of around £30,000, not to mention the price of installation and maintenance. Using normal electricity, powering a 35-watt street lamp 12 hours a day for a whole year only costs £16.25. Although this isn't using renewable energy, you can clearly see that it is a way more cost-effective method of powering street lamps. Therefore, we would not recommend investing in these energy-generating speed bumps, as it would take many years to make back the money spent in production. We would suggest investing in solar panels to power the lamps instead, as they only have an initial cost of around £2,000 and maintenance costs will be considerably lower, so are a much cheaper alternative.